All right, so we deprotonate first to get a resonance stabilized intermediate. Usually there is an electron withdrawing group on the carbon adjacent to the beta carbon. And then, so that you can stabilize the anion by resonance, then electrons kick down and the leaving group leaves to give you the elimination product. And if you make the steady state approximation in this carbanion, this deprotonated starting material, and then solve for that, you end up with this sort of kinetic scheme where the numerator has the alkyl halide and the base. The denominator has the conjugate acid of your base, and this K1 step, that's the backward step, and then K2 is moving forward. We're considering a couple of different scenarios, and there's different versions sort of the E1CB reaction. This one is called E1CBR, for where R is for reversible, and that's where the K1 step of going backwards is much faster than the K2 step. So K2 is slow, and when that happens, then this term of the denominator dominates. Your expression simplifies to this, and then we said if that's true, it's actually not the concentration of base only that matters, but the ratio of base to its conjugate acid, which you can reformulate as this, the Ka of the conjugate acid of your base divided by the pH. And that's a hallmark of specific base catalysis, which again, if you go back to our equation and say this equilibrium is fast and this is the rate determining step, then that makes sense for specific base catalysis. That is, the base removing step happens before the rate determining step. An example of a reaction that follows this kind of kinetics is actually this one here, where methoxy is a leaving group. If you want to ask why is the K2 step so slow, perhaps it's because methoxy is a cruddy leaving group. Okay, so that's a reversible version of the E1CB. The other sort of extreme we could imagine is if the K2 step is much, much faster than the K minus 1 step, and then we're going to call this E1CB IRR for irreversible, meaning that the protonation step is the slow step, is the rate determining step. And if you go back to our steady state approximation, if K2 is much faster than K1, then our overall equation should simplify to this, where we just have K1 times R times the leaving group times the concentration of base. And this should be, if you look at that, that's actually kinetically identical to an E2 reaction. So it might be difficult to tell the mechanism under this situation to distinguish it from E2. It's still a two-step mechanism, but the slow step is proton removal. This is the rate determining step in scenario 2, and then K2 is fast. However, there's one important hallmark, and that is that because the K2 step, where the leaving group leaves, is not in the equation, we expect changes in leaving group to not have a huge impact. So if a mechanism was this E1CB irreversible mechanism, then things you might do to change the quality of the leaving group shouldn't matter very much. So as an example of this situation, we've got this elimination reaction. It should look kind of similar actually to the one we just saw above. Here is the leaving group. And you can tell the people that did this were thinking about changing the quality of the leaving group by adjusting the identity of the X group. That looks like a situation for sort of standard Hammett analysis. We would add base, and in a slow step, we would remove the alpha proton to get the enolate conjugate base of our starting material. And then fast loss of the leaving group in the second step goes like this. And your products are this alpha beta unsaturated carbonyl compound and then this leaving group. Now again, notice that leaving group is the conjugate base of benzoic acid. That's straight from our Hammett analysis. And so you could imagine doing things to make that a better leaving group. For example, putting electron withdrawing groups here would make this more stable. Putting electron donating groups at X would make it more, would make it less stable. However, because leaving group leaving is not the rate determining step, because this deprotonation is the rate determining step, variations in X here don't affect the rate much. Okay, which is one of the ways you could tell that this isn't an E2 reaction. If it were an E2 reaction, if leaving group leaving were part of the rate determining step, then you would predict identity of the leaving group to matter more. All right, questions about that? All right. A couple other variations of, well, there's something about ion pairs, but that irritates me. Yeah, go ahead. Go ahead, Sam.
So, just looking at the two reactions, what makes it like irreversible for the second one?
Yeah, why is it reversible above versus irreversible below?
Yeah.
I'm not sure, other than if you did the kinetic experiments and saw that this one followed this kind of rate law, whereas this one followed this kind of rate law, but the leaving group didn't appear to matter, that would be the conclusion you would draw. As to what makes it that way, they both look pretty similar. I would say the biggest difference is the quality of the leaving group. If you look, leaving group is methoxy here. Leaving group is conjugate base of benzoic acid there. And if you look at the pKa's of the conjugate acids of those leaving groups, methanol pKa 16, benzoic acids, ew, I should know that number, I don't. In the 3 range or something like that. So this is a better leaving group here than this is, and that's consistent with the fact that for step 1, K2 is slow. K2 is the leaving group leaving step, whereas for 2, K2 is fast. So yeah, I think it's leaving. I think it's quality of the leaving group. All right. Yeah.
Does there exist a scenario where the leaving group is so bad where that becomes like slow enough for step, or you just not have the reaction happen in that case?
No, that's a good question, and that is, I think that is the situation in scenario one. The leaving group's bad enough that K2 is the rate determining step. Yeah. The surprise there is that the proton transfer is previous. Yeah.
So really the leaving group is what makes it either, I mean, it makes it one of these two mechanisms, right?
Right, that's the distinguishing feature between these
So
two different.
Even though it's not in the rate law necessarily, it does, like it does matter.
That's right. Even though, well, let's see, the leaving group is in the rate law in the sense that for both of these reactions, it appears in the starting material. The difference between 1 and 2 is that the K2 step is not in the rate law for here, but K2 is in the rate law there. But yeah, it's sort of the quality of the leaving group that decides whether you're in a reversible or irreversible situation. And that reversible and irreversible, that refers to this first step. Is the proton transfer reversible because the K2 step is slow, so you got plenty of time to go back? Or is the proton transfer irreversible because the K2 step is fast, and as soon as it's done, as soon as you do proton transfer, the K2 step happens?
Is it possible that you use a really strong base that it won't go back?
Right. So let's talk about that actually, like, because we've just dealt sort of with issues of what is the leaving group, but there's a lot of areas that you could vary to mess with this reaction, and there's an interplay between E2 and E1CB that we want to talk about. What if you used a better leaving group? We've talked about. What if you used a better electron withdrawing group? What if you used a better base? To reason through this, we can actually draw one of these Moore or O'Farrell-Jenks plots like we've done previously. So I'm just going to draw a square. I think, no, sometimes on Notability, if you hold your square long enough, it'll actually make a pretty square.
I just hate it because whenever I'm trying to draw molecules, I like to hold my pen on the page and then
Oh.
snap to a line or a triangle, and I'm like, no.
I guess that's all we're going to get, folks. Maybe I turned off the auto shape feature. Okay, so in our upper left-hand corner, we're going to have starting materials, base, and then leaving group. And then, let's see, in the lower corner, we're going to have olefin product, leaving group having left, and then conjugate acid of the base. In the upper right-hand corner, this x-axis is going to represent extent of deprotonation. So 100% deprotonated is going to be this intermediate, the conjugate acid of the base. And then in the lower right-hand corner, we're going to have, or rather along the y-axis, we're going to have extent of leaving group departure. And so this will be leaving group leaves prior to deprotonation. And we'll still have the base here in the lower left-hand corner because we haven't removed the proton yet. All right, so starting materials products, and then in blue, I'll draw a line that represents sort of the E2 pathway. And we'll put a transition state there, just sort of arbitrarily in the middle. for this particular E2 reaction, we're envisioning a transition state that is about 50% deprotonated and about 50% leaving group departed. Probably about 50% pi bond having formed. Okay. The nice thing about this plot is that it presents the E2, the E1, and the E1CB as parts of a continuum. So if you sort of follow along in orange, we'll show the pathway that's the E1 pathway. Where, as we talked about, leaving group leaves first, and then we remove the beta proton. This is similar, this is analogous to SN2 versus SN1 pathway. In the substitution case, though, we didn't ever have anything up on this upper corner because that would be nucleophile attacking before the leaving group left, and we don't do that with carbon. However, with elimination reactions, it's totally reasonable, and in pink I'll map out the plot that goes deprotonate first, and then the leaving group leaves. So this is sort of the E1CB pathway. And now using sort of the tools that we've used before to think about these free energy landscapes and how they might bias a system to one pathway versus another, we can think about what would happen in each of these situations. So let's do sort of an easy one first. Let's say the situation is we use a better leaving group. So we want to now highlight all of the times where there's a leaving group in having left in either of these corners. So I see a leaving group here and there. Using a better leaving group, using a better leaving group means that wherever the leaving group is in our diagram decreases in energy. So that would mean the effect of step one, using that good leaving group. Let's see, doesn't want to give me more colors, fine. Would be to take both of these corners and move them downward. All right, so just a review from our chapter where we discussed free energy landscapes. When you move corners of this plot up and down along the diagonal, either starting material or products, you see what's called a Hammond, I can't write that, can I? A Hammond effect, which means if we lower the energy of the product, the transition state resembles the product less, the transition state resembles the starting material more. So the impact of this change is going to be to move the transition state earlier away from products. In contrast, the off-diagonal positions, those have what we call an anti-Hammond effect, which is annoying. It just means backwards from Hammond. I like to think of it as marble on a sheet effect, held at all corners. If I lower the lower left-hand corner, the marble's going to be pulled in this direction towards that corner. So, and then both of these effects add together in sort of vector fashion, and the sum we'll use with this dotted line puts the new transition state here. Okay, and the new transition state we'll mark out with these dotted lines has the same extent of leaving group departure, but less deprotonation necessary to get that much leaving group departure. That's a funny kind of counterintuitive conclusion. You would think that if you use a better leaving group, that in the transition state, the leaving group should be more left, more gone, or whatever. But it turns out that if you use a better leaving group, the way you see that in the kinetics is that the leaving group's better, so you don't have to deprotonate as much for it to leave. Leaving group's better moves us a little bit more in the E1 direction for our transition state. Yeah?
When you say you don't have to have as much deprotonation for it to leave, do you mean like a certain percentage of the population of molecules, or are we talking like in a very vague?
We're talking about the transition state. If in starting material the proton is 0% removed and in the product it's 100% removed, in the transition state, how much is that bond broken? Yeah. Okay. So using a better leaving group is gonna swing your pathway more to the E1 direction. Now we can do a similar sort of analysis with a ton of other different issues. For example, let's consider what if we use a better electron withdrawing group on the beta carbon. So in this case, let's just replace all of the R's with electron withdrawing group. That's kind of sad. EWG, good. And now I guess I'll erase the stuff we did previously so that we can draw on our diagram again. Okay. So, better electron withdrawing group on the beta carbon. What do you predict that's going to do to each of our corners? I've got an electron withdrawing group here, 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 and here.
Sorry, what is 2 again?
So 2, sorry, is what if I use a better electron withdrawing group? What do you predict down here? I mean, yeah, although maybe it's subtle because it's not exactly directly attached to the positive charge, but sure, you're making something positively charged and it's already electron poor. So, yeah, that effect would be an increase in energy. What about here? Okay, that should be a decrease in energy. Why? Because you're stabilizing the negative charge. I'm not totally certain how it should affect starting material or products. I don't really see a big effect there. All right. So mostly the, excuse me, mostly the impact of the electron withdrawing group is an off-diagonal anti-Hammond effect. We're going to raise this corner and we're going to lower that corner. Both of those are going to have the same effect, right? That's going to push this transition state this way, which is going to get us way more deprotonation and way less leaving group departure, which is sort of the definition of an E1CB reaction anyway. All right. How about using a stronger base? So let's see, I'll just erase some of So item 3 will be, let's use, okay, maybe I'll just write down the conclusion. Better EW, electron withdrawing group on the beta carbon. We see more deprotonation, less leaving group leaving. And then, yeah, let's use a better base. That is a more reactive B minus. So we have to identify all the times we've got that base, and those are the upper and lower left-hand corners. So more reactive base is going to be moving up or lower in energy for your base. Should we be going uphill or downhill in energy? Okay, let's see. If the base is more reactive, that means its conjugate acid is weaker. So more reactive base is actually higher in energy. A more reactive nucleophile has less stable electrons that are more able to remove protons. Does that make sense? Yeah? Okay, so in the upper left-hand corner, we're going to have the Hammond effect. This is going to, we've raised the energy of our starting material. That's going to make our starting material resemble the transition state more, or rather the transition state resemble the starting material more. Using a more reactive base makes the transition state earlier. In contrast, over here in the lower left-hand corner, using a more reactive base should result in an anti-Hammond effect. We're raising this corner of the sheet. The marble should roll that way, perpendicular to the corner that we, whoop, there went the eraser, perpendicular to the corner where we made the change. The net effect will be to move our transition state here. Overall, compared to where we started, we have the same extent of deprotonation, but now less leaving group departure. Again, that's kind of counterintuitive. We think that using a better base should cause more deprotonation to happen, but actually we see the same extent of deprotonation, but less leaving group departure required for that deprotonation to happen. So using a stronger base pushes us a little bit more towards the E1CB side than the E2 side, because again, E1CB is all about you deprotonate first and then the leaving group leaves, and we are decreasing the extent to which the leaving group leaves. Okay. Any more you want to talk about on those sort of E1, E2 issues? Okay, next is regioselectivity. So what we mean by that is when you have an elimination reaction and there's more than one possible beta proton, what is the product that you get? So what do you remember from your introductory OChem class? Think back deeply. There was a rule. Sometimes if I taught your OChem class, I'm not big on memorizing rules. But there is a rule.
I remember looking at your study guide taking this exam, and I can almost see the word in my head, but I can't.
Okay, it's like Markovnikov, a dead Russian guy.
Yeah.
So yeah, Zaitsev is how it's spelled in this text. You may have seen it. Yep. So the Zaitsev product is the more substituted olefin. And generally that dominates in E1 and E2 reactions. For E1CB reactions, the regioselectivity is entirely dominated by that electron withdrawing group, so the issue of substitution really doesn't come up. Your most acidic proton is the one that gets removed, and that's defined by where the electron withdrawing group is. Man, I feel like a rumble with my voice. It's like so deep. It's kind of cool. Right. So what's the rationale for the Zaitsev rule, which is the more substituted olefin dominates? I'm going to give you an example of this in the context of the E2 reaction and an E1 reaction. Here is an E2 reaction. You look at those conditions, you're like, why doesn't SN1 happen? I think it probably does. I think, though, they're just reporting here the elimination product ratios. On the left, we have the more substituted olefin. On the right, we have the less substituted olefin, and it's a sort of 2-to-1, almost 3-to-1 ratio. Okay, and for, let's see, I don't have a E2 reaction. Hold on. Yeah, anyway, I don't have an example E2 reaction. For the E1 reaction, why should, this has troubled me a little bit. If you remember, we could draw an energy diagram for the E1 reaction. The transition state that determines the rate is leaving group leaves, right? So this is the leaving group leaves, and then this is the deprotonation step, right? And the leaving group leaves is the rate determining step. So why should the substitution pattern of the alkene matter at all here? What do you know about more substituted alkenes? They're more stable, okay? Is this a situation where product stability matters? It would depend on whether this is an equilibrium or not, right? Whether it's reversible or not. Under reversible conditions, the major product is the more stable product. And that's a convenient explanation here because the more substituted product is the more stable olefin. And that's because of the electron donating character of alkyl groups when they're next to sp2 hybridized carbons. That's also because of sigma to pi star hyperconjugation with the adjacent carbon-hydrogen bonds that are adjacent to the pi bond. The explanation your text uses would apply when this reaction is not reversible. And they're arguing basically that in this second transition state, there's a buildup of, the olefin begins to form as the proton in this transition state 2, not the rate determining transition state, as the proton is being removed from the carbocation, there's a buildup of olefin or pi bond character in between these two carbons, and that what stabilizes a pi bond must also stabilize this transition state, and therefore it must be faster to form the more substituted product. I'm not sure how much I believe that, in part because this is not the rate determining step, and so to argue for some kind of selectivity to be controlled by not the rate determining step is a little bit troubling for me. The explanation I often use is that in this E1 reaction, and you're following sort of along with the solvent, following along with the mechanism, the thing that's the base here is either the departed leaving group or the solvent, which means in the end, excuse me, you either make HBr or you make the conjugate acid of ethanol. And of course, we know that we've just talked about earlier on in this chapter that you can add acids to olefins. And so my guess is that the explanation I prefer here, again, sort of departure from your text, is that in a reaction that's reversible, the thing that matters more is product stability. Okay, for the E2 reaction, which is irreversible, generally using a strong enough base, you remove the proton and the leaving group leaves, and it's strongly exothermic. That one transition state, then, we are arguing does have a substantial buildup of pi bond character in between the alpha and the beta carbons, and therefore the transition state that leads to the more substituted olefin should itself be more stable and therefore should be faster. And that's an explanation that I think works pretty well. Okay, another thing you should know about olefin regioselectivity is that in contrast to the Zaitsev product, the Hoffman product is the less substituted olefin. And there are situations where you can see this happen as well. So when are some times that we see the Hoffman product? If you use a bulky enough base, you can start to see evidence for removing the less substituted, removing the proton that gives you the less substituted olefin because of steric issues. Your text doesn't have really any examples of using bulky bases as a major determinant of regioselectivity, but it mentions that you can sometimes see that. And sometimes we're talking about small shifts in favor, sort of small changes that a second, but that would be because of sort of steric issues. A second issue is if some beta protons are more sterically inaccessible, then you can start to see Hoffman product. An example of that is this weird molecule where you have sort of two different kinds of beta protons, and you're using not a very sterically bulky base. This is sodium hydroxide in ethanol. The more substituted olefin is this one, but that only forms in 14%, and by far the favored product is the less substituted one here. And the idea here is you're used to looking at tertiary carbons and thinking, oh, what a sterically hindered carbon, that's a T-butyl group, right? It turns out carbons that are adjacent to T-butyl groups are also pretty sterically crowded. This position adjacent to a T-butyl group is called the neopentyl position, and we would learn about this if we got to substitution in chapter 11. But even though this is a secondary carbon, if you put a leaving group here, you would not be able to do SN2 adjacent to a T-butyl group just because of sterics. Neopentyl SN2s don't work very well. Presumably for that reason, because of that adjacent T-butyl group, we could build a model and see. Now we're going to do it, aren't we? Yep. Let's build a model and see. I think even if this isn't in the Spartan database, we'll be able to look at it from a space filling point of view. It's going to really like us. There we go. Okay. So you see on the left is our T-butyl group. Right in the middle is our neopentyl carbon. Here's the leaving group, and here are the less substituted beta protons. Now I'm going to turn this into space filling. And you can see how very crowded that proton is, that it's very close to these adjacent protons from the T-butyl group. Both of them are. This one's almost literally bumping into that adjacent carbon. So it's easier for a base by far to come out and attack these protons that are just on methyl groups that are quite accessible. All right, so subtle steric issues can lead to some of these things. And of course, the introductory OChem student wants to know, how can I know when that's going to happen so I can avoid getting a question wrong on an exam? it's less about that, and it's like, how can you rationalize a result after you take the NMR and you see, oh shoot, that's not my desired product. The olefin's in the wrong place. Can you explain it? And in this case, yeah, it's because of steric hindrance. Let's see, there are some leaving groups that preferentially favor Hofmann regioselectivity. So some examples of this are quaternary ammonium leaving groups, and also sulfonium leaving groups. So let me see if I can give you an example of that. This is a sulfonium group, and then this is a quaternary ammonium group at the 2 position of a butane ring. The leaving group I'll just highlight in green. It can leave as something that's neutral, so that's not a bad situation. And then, so for the sulfonium group, they're using sodium ethoxide in ethanol. And then here's the Hofmann elimination product versus the Zaitsev elimination product. 74% for Hofmann, 26% for Zaitsev. And then the elimination of this quaternary ammonium group gives you the same products, and the ratios are even better, 95% for the Hofmann product and only 5% of the Zaitsev product. So the question is, why does it turn out this way? What do you think? Yep, so sterics is a big thing. Sterics is it's a bigger leaving group, and so the base will be biased towards the less hindered carbon, less hindered beta proton, simply to get away from the leaving group, which is very large. So yeah, why reason 1 is because of sterics. And sulfur is also quite large. It's not tetra substituted like the nitrogen is, but it's also quite large. There's also an electronic effect. I mean, if it's not sterics, it's electronics. So, which is kind of a lame answer. But these positively charged groups that have positive formal charge on them are strongly electron withdrawing. And what that does, I don't know what I'm trying to do there. I'm trying to erase. There we go. And another way of thinking of those leaving groups as being strongly electron withdrawing is that the carbon leaving group sigma star is decently low in energy. Remember, electronegative things move things downward, right? And that withdrawing effect puts, anyway, the way your text explains this is this withdrawing effect puts a substantial partial positive charge on the alpha carbon and to a lesser extent on the beta carbons, but that the more alkyl groups, so these are both beta carbons, right? The more alkyl groups you have on those beta carbons, alkyl groups are electron donating. So the presence of alkyl groups attenuates, that is, decreases the amount of partial positive charge you have on the beta carbon, and that makes the beta proton less electrophilic, less prone to being attacked. That's kind of, I feel like it's a little bit hand-wavy because why doesn't that happen always? But I think the argument is that these leaving groups, the sulfoniums and the ammoniums, are so strongly electron withdrawing that the impact of having delta plus on not only the alpha carbon, but also on the beta carbons matters. And the more alkyl groups you have on your beta carbons, the less electron poor they're going to be. All right. And let's see, we need to talk, there's maybe some more data I'll show you next time. There's some stuff about E2 or stereochemistry of eliminations, orbital considerations, syn versus anti-periplanar elimination. And that, I think, will take us through the end. So we're not even going to get to imine formation. Oh well, you know all about that anyway. The whole point of this is showing you that the world is more complicated than you thought it was, and to approach with caution.